All right. Hello, everybody. Calling from Pasadena, California at the Caltech campus. Welcome to Making AI Possible. This is a podcast where we explore how today's most advanced AI and machine learning research is shaping the world beyond the lab. I'm your host, Nicolas Baudouin, and today's episode takes us far beyond the walls of industry and straight up into the stars. Today's discussion centers around how machine learning is transforming how we observe the universe. And really, what we're going to do is we're going to peer into a Palomar Observatory with our guest, who discusses the Zwicky Transient Facility, ZTF, which is a system that scans half of the northern night sky every single night and uses various machine learning algorithms and advanced AI capabilities to detect and classify hundreds of thousands of celestial events in real time. Joining us is Dr. Matthew Graham, who is a research professor of astronomy at Caltech and the project scientist for ZTF, he's one of the world's foremost experts on massive scale time series data, anomaly detection, machine learning, not just to study the universe, but to essentially automate its discovery. So whether you're building the next fraud detection or building an agentic AI system, I think you'll get a lot out of today's talk. So let's get started. Matthew, I'll do a very brief introduction, and then I will let you take it from there. He has a BA in physics from the University of Oxford, a PhD in astrophysics from the University of Lancashire, and 22 years of experience at Caltech, starting his career as a computational scientist, and is currently a research professor at ZTF. So, Matthew, I will let it take you away. Thanks for joining us today.
Thanks very much for having me, Nick. Yes, so my background as, growing up as a kid, I was always interested very much in astronomy and physics, and actually my dream job was to be a researcher at Caltech. We're growing up in the UK because I'd heard of Feynman and there's the Voyager stuff with JPL in the late 70s. I'm of that vintage. So I was really happy when I came here in 2003. But yeah, so I was one of those. I was never an amateur astronomer because the UK is not really good for that. But I was one of those who was always reading the latest physics books or the latest, this is what we're thinking is happening with the Big Bang type stuff. And so physics and then into cosmology, or observational cosmology, which was what my thesis was on for my PhD, where I was doing early sky survey work, and that's sort of been basically the backbone of my career since then.
Excellent. So let's dive into a little bit of the infrastructure and facility to set the tone for today's
Yeah,
discussion.
sure.
Can you go into ZTF telescope itself? Tell us how Palomar Observatory relates to the conversation that we're about to have.
Yeah, sure. So Palomar is a unique place for a variety of reasons, but it's the crown jewel in Caltech's astronomy portfolio. So we have the 200-inch telescope there, which was the world's largest telescope from 1948 up until the early 90s. And we also have the 48-inch Samuel Oskin Schmidt telescope, which is a survey telescope, which is the same vintage. It took its first images on the 30th of September 1948, but it has a corrector on it, so it has a very large field of view. So it can look at a large area of sky in a single observation. And back in 1948, when they started using it, when Fritz Zwicky, who was a Caltech researcher for many years, professor for many years, and really the father of sky surveys at Caltech, which is part of the reason why ZTF is the Zwicky Transient Facility, they were using photographic plates. So you would put a photographic plate in, you'd expose it for about 45 minutes, an hour, then you take it down to the dark room, develop it, and then Zwicky was already interested in supernovae. In fact, he's one of the people who coined the name supernova. And he had the world record for discovering supernova for many years. I think he found 130 or 140 over 35 years. What they would do is they would take these old they'd take a photographic plate I've taken now, and here's one that I took some weeks ago, and they put it into what's called a blink comparator, which is a mechanical device which allows you through the optics to switch between looking at the two, and you're looking for things that are blinking there that weren't there before, or something that's moved, something like that. It's how Clyde Tombaugh found Pluto in 1930 with Lowell Observatory. It's a good, solid technology. Um, so, but the 48 inch has been a survey telescope for, the last 76 years. In the late 90s, early 2000s, they switched from having photographic plates to digital cameras, CCD cameras. So when I came to Caltech in 2003, the Palomar Quest survey was just getting going, which was the first digital sky survey using the 48 inch. And we haven't really looked back since then. The Palomar Quest survey they switched cameras out, and that became the Palomar Transient Factory. And then we replaced the camera again with the Zwicky camera, and that became ZTF, which we started. First light was October 2017, and we started the survey March 17th, 2018. And we've been every night since then. I mean, modulo the weather and one or two camera problems, but virtually every night since then, we open up and we start observing the night sky. And we just do that every night, every night, every night. And during COVID, because I should say, the 48 inch is fully robotic now. So there's no, someone needs to make sure the power's on in the morning or the power's on in the afternoon, and then that's it. No one else needs to do anything. It's fully roboticized. And so during COVID, we were just going happily, we're getting data and whatever, because no one needed to do anything. It was just, very, very, very optimized. The other telescope on Palomar that's of use to us as well is there's a 60-inch mirror, which is also fully roboticized. And we have a low resolution spectrograph on there. So we can get follow-up spectra of things we've detected with the 48 inch. And in fact, what we have today is a very automated pipeline that an observation is taken with the 48 inch. It's brought down to here at Caltech. It's reduced over at IPAC. Within 20 minutes, we have the data from that observation. We know the things that have changed in that observation from when we looked there before. And if there's anything of interest, it'll automatically get scheduled, sent to the 60-inch. It'll take an automatic observation of it. That'll get reduced. Machine learning does the classification, and then that's announced to the community. So that whole process now is fully automated. So that's why Palomar is so good, that we have these combined facilities that we can do. If we want an even better spectrum, we can automatically insert it in the queue for the 200-inch, which is still done with night observers, but it may be a grad student who's saying, what am I observing tonight? Oh, there's a new entry that's just come in at number 3. I'm going to move on to that now, and that sort of thing.
So in my very nascent mind of astronomy, I think about this. I think of someone going like, "Oh, that's a cool object. Let me go look at this object. Okay, let me look at this." So when you say you have the Caltech grad student, is there a central database that they have assigned regions that they're looking at?
It's not regions. What will happen is that I mean, we regularly apply for time on the both at Keck and for the 200-inch for follow-up programs that ZTF is feeding. And it's part of the grad student training or even the undergraduate training that they will do observing. And these days it tends to be all done remotely anyhow, so they can just sort of sit at their laptop at home or whatever and do it. I was doing that actually on Sunday night with the 200-inch. I was at home observing. But what we have is we've built infrastructure. We have a system called FRITS, which is in the terminology of our field is called a marshal, or it's called a broker. And it's a knowledge management system that allows us to keep track of objects of interest, whether they've just gone off now, or whether they went off 6 months ago, and we've been tracking them since then. And we can use it for filtering, for scanning through, for annotating things that are of interest, adding more data from different things that we find. There may be something that went off when we go, okay, well, we'll get a spectrum of that, but we also want to get an X-ray observation of that with the Trangia satellite or something like that. And when that data comes down, that'll get uploaded in that. So, each object of interest has its own splash page. So you can go and look at it and go, oh, right, that's what we've got about this. Oh, and my colleague Jesper Solomon in Sweden has made this note about this, and my colleague in France has made this note about this. Oh, they're discussing this, and here's my opinion of what it is, and that sort of thing. So so that piece of software or that piece of architecture really is essential for knitting this whole thing together, because we've got ZTF is probably 150 to 200 people around the world, all told, involved. Certainly at its height, it has been. And when you've got people in Taiwan who are looking for asteroids, and you've got people in Sweden who are looking for supernova, and we're looking for AGN or whatever tidal disruption events, coordinating that needs something, and that's very much at the heart of this system. And there's machine learning and AI underlying that for quite a few tasks.
So to take it back for our
Yeah.
listeners, you survey the night sky.
Yeah.
You bring back the images.
Yeah.
What does that amount of data look like? Like, are we
Yeah.
talking floppy disk 1999, or are we talking terabytes of data being streamed with Kafka live?
Yes. So bear in mind, we are an old survey now. So, the camera was built in the mid 2015, 2016 period. So it's all 10 years. Um, uh, we take about somewhere between 500 to 1,200 observations a night, depending on what time of year it is.
No,
So
it's an observation, like a snapshot, or is
yeah,
observation an event?
it's a 30-second exposure.
Hmm.
So imagine it's a regular camera. You set it for 30 seconds. You hit click open, and then the shutter closes, and then the telescope moves, and then it goes to its next 30-second exposure.
So one area of the night sky will have 30 seconds to
Yeah,
essentially reveal
yeah,
itself.
yeah,
Okay.
yeah, yeah. So we take a 30-second exposure, and as I say, night in June is we've probably got 6-7 hours of observation. A night in December, we've got 12 hours of observation.
Right, right.
So that's why we get between 500 and 1,200 observations a night. So the data streams down. It's actually sent via microwave link to San Diego, and then on regular internet up to Pasadena. And all told, we take 1.4 terabytes of data a night compressed.
Wow. And so how many events, how many alerts,
Right.
anomalies are you looking at with that?
Right. So each single 30-second observation is 47 square degrees of sky. So if you think that the moon is half a degree across, so it's about no, I'm going to get this wrong, 14 moons by 14 moons in terms of the size that we actually look. So the photographic plates that Zwicky used to took was only 25 square degrees, because that was the limitation of the physical size of the plates that he could do. We actually use the full focal plane that's available to us, and so ours is 47 square degrees. 30-second exposure, we probably find 1,000. So what we call them transient events, and each transient event we treat separately and has a binary data packet associated with it, which we call an alert.
Mm-hmm.
So a single observation produces about 1,000 alerts. So if we're doing 500 observations a night, that's 500,000 alerts a night. Up to maybe 1 million alerts a night in the winter, or depending which area of sky. Now, what do we mean by alert on a transient? So I take an observation now, I go back to the archive, and I say, what do I think this area of sky looks like in some sort of static sense? I have a reference image, and I take computationally one image away from the other. I create what's called a difference image.
Mm-hmm.
And that should leave things that have changed. They've either got brighter, or they've got fainter, or there's something there that was not there before, or something that was there before is not there anymore. So it might be moving. There might be some tracks in there as well, because if it's a satellite, it'll have a fixed position. It'll smear across. And so each of those detections, we then do an assessment of its reliability, how realistic it is, whether we think it's a data artifact or not. And we have machine learning for doing that. And anything that's a 5 sigma detection, in the sense that we think it's actually very real, we then say, okay, that's an alert. Now, when we started out back in 2018, when we started doing the alert stream in June of 2018, we were very conservative. We said 10 sigma. We're not doing, we're just absolutely really low hanging fruit. And we always had this notion, oh, as we get more experience and the community gets more experience and we have all these more sophisticated, we'll turn it down until, we'll be doing 2 sigma at some point, which would be millions of alerts. Like we've never done. We've always stuck at 5 sigma because that rate itself has been enough to keep the community completely happy. Now, the Rubin Observatory, which is just finally finishing completion in Chile, is a 6.5 meter telescope, effective area. It's an 8 meter properly, but its effective collecting area is 6.5 meter because of the design of the mirror. And it will produce an order of magnitude larger. It will produce 10 million alerts a night because it goes, its field of view is only 9 square degrees, so it's smaller, but it's a larger light bucket, so it can go much fainter magnitudes. And so there'll be more objects that it'll see changing and that sort of thing. So ZTF is about a 10% of the legacy Sky Survey Space and Time, or LSST, which is the server that they're going to be running starting next year, early next year. So we're talking about 500,000 to 1 million alerts a night. A single observation, as I say, produces about 1,000. Now, a lot of those actually, I mean, we say that they are changes in brightness of an object. There are a lot of objects out there which are stars or faraway galaxies, supermassive black holes, which are permanently varying. So a lot of the things that we see are actually are variable stars or something like that. And part of the filtering then of this large alert stream is trying to figure out what is transient, what is of a particular type, and what's associated with, oh no, there's a star there always. It's not of interest to me, but it may be of interest to someone else, but we'll flag it up as one of these or classify it as one of these.
Can you give an example of something that would be very transient, that'd be very
Yes.
quick? Maybe you can discover this in a couple of nights versus something that needs more of a time series based element
Yeah.
that's going to take longer to discover.
Yeah. I mean, so we talk about the dynamic night sky, and there are very fast transients. In fact, there's a whole subfield that we're not set up for, where people are looking at things that are varying on, less than a second. Our ideal time slot is, things that vary on minutes to hours to days.
Mm.
So a supernova, I mean, one of our most common transient is our supernovae. So these are the end stages of stars where the star collapses and explodes in a very bright flash. And the rise time, which is because it goes up and then fades, and that's the sort of characteristic signal we're always
Hmm.
looking for a lot of the things. The rise time is maybe 5 to 10 days, depending on the type of supernova. Maybe for certain types it'll be slightly longer, and then the decay time is a couple of months. And so the most common type of supernova is a type 1a supernova. And people are really interested in finding these because these are the things that can be used for measuring the acceleration of the expanding universe.
Mm.
They can be used as what's called a standardizable candle. And we've found about 10,000 of those now. And we have the advantage that, so you get what we call the light curve, the time series, but you also then want to take spectra to make certain that you actually have found what you think it is. And so what happens then is, if it looks like a type 1a supernova, it gets sent over to the 60-inch for the automatic
Mm.
spectrum to be taken, and then that gets classified. And I said that entire process now is fully automated. Even the reporting to the community data archive for supernova. So you can wake up in the morning and go, oh, we discovered 4 supernova last night. I wasn't aware of it. It's all happened. The data, on a perfect night, it's an hour and a half maybe from discovery through to classification through to reporting.
Can you talk a little bit about what that technical pipeline looks like?
Yeah,
Keeping in
yeah,
mind, we have a lot of folks in industry specifically working in anomaly detection
yeah,
fields. These can
yeah.
be anomaly detection for, say, roller coaster maintenance, or it can be medical based IoT sensors.
Yeah.
Kind of curious what your pipeline
Yeah.
looks like.
So our first, so essentially, to hone it down to that this is a viable supernova candidate. That's really the first goal that we're after, because then that will be sent over to the 60-inch for spectrum take. So the first thing is, okay, we got a detection. We need to make sure that we're confident that this is not. We have a filter called a real bogus classifier. We want to make sure that this is not a data artifact or a glint or a piece of space junk or whatever that just happens to look right, first of all, in the detection. And so we use a convolutional neural network, a very simple one because we wrote this back in 2018. And so we use a VGG6 based network. But it did better than in PTF, they had a random forest algorithm for doing this, which was state of the art. When we tried that with ZTF data, it was doing okay, 85%, 85% accuracy, but we need to be, because of the rates, we need to be much higher than that. And so we use this, we tried a convolutional neural network, and that system is called BRI, and which is the Afrikaner word for barbecue, but it has AI in there. We were looking for words with AI, and someone said, "Oh, Bry, yeah, okay, isn't it?" So it is.
We're going to reach, Matthew, we're going to reach a point where all the good model names are taken
Oh,
at
I
one
know,
point.
I know. But the advantage of Bry is that the real bogus score, we have 1% false positive, false negative, depending on where we do that. So that was so much better than what was done before. So that gives us real confidence, first of all, then that what we're looking at, what we're working with, is a genuine astrophysical transient rather than some sort of anomaly.
Right.
I mean, so 1% when you've got 100,000 still means you're going to get, 1,000 junk, but it's an acceptable trade-off. And so when we know it's a real transit, and then I was talking about how we have these binary data packets that we create for each alert. And actually, so that has the real bogus score in it, but it has other things in it as well. There are a couple of other machine learning classifiers, deep learning classifiers that we've run over the thumbnail images we put in, which allow us to determine whether, is there a galaxy or is there a host galaxy nearby? Because supernova tend to be associated with host galaxies rather than it being some free floating thing with nothing nearby, which could be something very distant, or it could
You're
be,
right.
whatever. And so we have things which give us context about the environment. That's a very important piece of information for us doing the interpretation. We also include things like looking up in other data archives. What's the position of the nearest solar system object to this? Because this could be a new lump of rock that we're seeing, or it could be, or it could be something that's already known and it just happens to be there at the time. And what's the nearest location of the nearest star from other catalogs and things like that. So that's all put in. And what happens is using this Fritz system, our broker Marshall system, people write what we call filters against the alert stream. So they're looking for alert packets which have particular characteristics. So it's a high real bogus, and it looks like a supernova, and it's got a host galaxy nearby. And we also include a 30-day rolling time window of observations at that particular position that we've seen in previous nights. So if you've seen nothing there for the last 30 nights and suddenly you see that first data point, oh, that could be. And there's a whole game in getting what's called infant supernovae, that we identify them as quickly as possible because we want to see what they're doing during that
Mm-hmm.
rise before pre-peak, because that tells you a lot about the environment and the physics of what you're seeing going on. And so there are people who've honed particular algorithms to look for those sorts of things, and trained models for doing fast identification of these things. And so that takes us to, so we filter down to say, okay, we think this is a good 1A supernova. It gets scheduled on the 60 inch. The 60 inch takes a spectrum. The spectrum is automatically reduced, and then there is another deep learning classifier which then looks at that spectral sequence. So it's it's like a time series, but it's wavelength versus energy. And it's been trained on sequential data for doing classification to say this looks like a 1A supernova, high probability. If it passes that, then it gets just reported through an API to the transient name service in Israel. So we have AI, machine learning,
Right.
or at least deep learning for classification, for figuring out what's going on, and all that at various points along the cycle. But a lot of all those systems have been trained by several years of grad students looking at the things and going, this is, this isn't, this isn't. So that's how we do our training set, which then we
Right.
report the grad student with the with the neural network.
We tend to think as compute being the blocker for effective machine learning projects, and really it's just the cheap labor of grad
Yeah,
students labeling things.
yeah. Yeah, the actual, the imputation time or the inference time is so fast. That's not where the problem comes. The problem comes in the training. That's the computational cost for a lot of this.
Mm.
Not only in terms of CPU or GPU hours, but also in forming that training data set. And what it turns out is that, the quality of your classifier is actually, it's probably not so much dependent on the architecture you're using. It's really dependent on the quality of the training set that you're putting in.
Yeah. Having worked in industry with a lot of anomaly detection use cases, mainly in manufacturing, I found that a lot of corporations go full in to kind of a full court press on different types of predictive maintenance. But then when it comes to getting too many alerts for their sustainment engineers, you get this alert fatigue.
Yeah.
Did you find that there was an alert fatigue? So say you're at five sigmas and you're like, oh, let's just try 2 sigmas tonight, where people just like, that's it. Dr. Graham, is full of it. He's just sending us too many things. We're not going to trust him. How did you deal with alert fatigue?
Well, it's really interesting because I thought that we would have alert fatigue. I really thought that, at some point we're going to reach the point where actually I always thought of it more in the 24-hour news cycle model. Right. What is interesting now, and how do I oh no, that's the new one. That's the new next thing. Oh no, this alert is coming. That's more interesting than that one.
Literally shiny object syndrome.
Yeah, no, exactly. The problem is when you've got, let's say we find 5 supernova a night, something like that on a good run. How do we need to keep track of all of those over the next several months? Because we need to know what they're doing, because ultimately they're going to end up in some big sample for statistical analysis. It's not as though, oh, we found that and we just go, okay. So, so there is this management process, and it is, how do you maintain interest in, oh, that looks so much more interesting, that thing we found 2 weeks ago, and we know what that's going to do, and maybe it will, maybe it won't. And
you're still around a 1% false positive rate for these?
Yeah, probably something like that. So I always thought it was going to be much more along those lines. And I think what we thought we would see happen is that the bright shiny or the new shiny would wear off. That after a point would be, there's this, people have said, no, we have a motto of, no, leave no supernova behind. Or leave no transient behind. And it's sort of, no, come on.
Please tell me you have a t-shirt that says that for your team.
I wish I had, actually. But one of the problems is that it's not just the discovery. The discovery is the easy bit. It's the harder bit is actually what you're going to do afterwards, which is where the real science lies. And that requires a lot of resources, and we're resource limited in terms of what other big telescopes do we have that we can use, and facilities like that. And we can't chase that many objects going forward. And this is an even bigger problem for Rubin in coming years, where their rates are 10 times what we're looking at.
Yeah.
And they won't, and it's much harder to look at the really faint things that they're after. What's good about ZTF is we're because we're a small telescope, the stuff we discover is easily to follow up with other facilities that, that are available to the community.
Yeah.
But we always thought, we thought, okay, when you get to 1,000 supernovae, will be done. And, and then we'll move into what we call population studies, where the papers will be written not about individual objects anymore, but we're still in this. We're writing papers about individual
Mm.
objects. We're still in this is the new shiny because, I mean, they're all valid because they're all exciting, interesting, and telling us, and it's somewhat different from that, and it's different from that, and so it's all new. But we're still, and I'm surprised. I'm surprised we haven't moved on yet. I would have thought. I mean, I'm pleasantly surprised, but yeah. So I think the alert fatigue hasn't kicked in yet because there's
Mm.
still enough of a new shiny, and there's still enough people who are willing to do the individual object stuff, and they're still interested in it that they will. I think we always thought it would come with CTF, and it's one of these things we always think it's going to come with the next thing, and then we sort of adapt. And I think it will come with Rubin. I think when
Hmm.
it's 10 million alerts a night, and most of them are going to be handled probabilistically, or they're going to be, you know, um, you're never going to look at the data. You're never going to get a follow-up spectrum. It's going to be a data point in a plot
Hmm.
somewhere, a high dimensional, very informative plot, but it's still just an individual data point. Um, we're going to move away. There will still be new shiny, but they're going to be the really rare things. It's going to be much more like JWST
Hmm.
type of new shiny rather than, sort of rank and file new shiny, I think. Um, so we haven't, I'm surprised we didn't get there yet, but I think we haven't. Um, you know, um, and the other reason actually that we've managed not to is because we have, as new AI models, new deep learning models have come along, we have adjusted to them to improve our capabilities. And so there's more that we can do, and there's more than we can farm off onto so automating bits of it, so that we can focus on the things that are of more interest, and
Mm.
some of the less interesting ones can be left to the computers, as it were.
Well, you'll be chagrined to know that one of our listeners just sent me an email with I think it is a Gen AI created T-shirt saying "No transient left behind." So if you need the rights, I can be a broker to that. I don't know what platform, but speaking of generative AI, kind of the elephant in the room. You talked about probabilistic processes leading to discovery. Has the transformer model poked its head in any of the processes that you've been looking at?
Um, yes, it has. I mean, we do use transformers for um, so we don't use them for the real-time stream yet, because we've not really found a need to. Where we have used them is actually so I say we generate 500,000 alerts a night, but we've actually got time series for about 3 billion astronomical sources. And so because we've been looking at the sky every night, so we've got 8 years worth of, well, any object on the sky, we can give you what it's been doing for the last 8 years in different astronomical filters, a green
Mm-hmm.
filter, a red filter, a blue filter. Um, and so we have, huge numbers of time series that we want to process and go through. And I mean, they're either supermassive black holes, or they're galaxies, or they're stars. And so people who study the Milky Way are very interested in the, 1 billion stellar time series we have, and what have they been doing. I'm interested in supermassive black holes, and we've probably got about 5 million, 10 million of those in there. And so one of the things that we do there is we do bulk classification. And because these are complicated or complex time series, we think about statistical representations which allow us to classify this versus this, or how do we do featureless representations, use the time series themselves, and what's the appropriate. So there's a lot of representation learning that we've applied to this. And actually, we have used transformers, a transformer-based model for identifying supermassive black holes.
Mm.
My Shimon Nakanishi, who was my postdoc up until recently, and he's gone back to Poland to another position there now, but he applied a transformer model to go through 2 billion ZTF time series to find 5 million AGN.
It's a real needle in the haystack problem
Yeah,
right there.
yeah, yeah. And so we are so and there's a strong movement in astronomy generally now for foundation models for representation learning and for multimodal representation learning. So how do I combine images with spectra with whatever,
Mhm.
and then map it into this common representation space, and then do maybe anomaly detection or stuff like that. And
Yeah.
so we have a dedicated machine learning group within the ZTF project, and that's sort of one of the things they are thinking about application on.
Do you think that there's going to be a day where the discovery of anomaly is automated, where you can just open up your computer and say, here is the anomaly, here's the description, ready to publish?
Um, yes, I think there'll be. I mean, I think a qualified yes.
I'm not going to hold you to this.
No, 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 no. I mean, I think the large language models are certainly getting better all the time, and with enough training, they probably could produce a reasonable paper. And I think the issue is in interpretation and explainability, to say this is what I've done and I think it's this, and for it to sound credible and consistent. So I mean, we're certainly at the stage where we can have an agent system which writes the short piece of text to send out about, this is here's a high probability candidate supernova that I discovered last night at this position with these characteristics and whatever. And so that's essentially what we're doing to TNS. So we've got that bit. So the next bit is, okay, here's the space, find the anomalies, and then try and figure out what they are based on what associations you can make. There are automated scientific discovery techniques for doing that um, in AI machine learning, symbolic regression or techniques like that,
Mhm.
or AlphaEvolve, which is the latest one that came out a couple of weeks ago. Um, you know, that you might be able, it'll link things together and maybe come up with a consistent story. I think we're not there yet. I suspect, we will see those.
Mm.
And they'll get more sophisticated as time goes on. Um,
So this is kind of the point of the show where we start talking about industry use cases
yeah.
and how your research has benefited industry and vice versa. Maybe you've used algorithms or pipelines that have come from industry. I also want to remind listeners that we have a Q&A capability. I've already seen a couple questions come in. And as we talk about the industry talk, Matthew, I'll start peppering in some questions. Don't worry, I'll keep it anonymous for who asked them. So, industry lessons. Is there anything that you have found in your last 8 years in your current facility or 22 years at Caltech that you have found and said, you know what, industry can learn for this, or something you saw in industry that helped with your own pipelines?
Um, so many things, I think. I mean, it's yes. I think so. What was really interesting is that in terms of computational infrastructure, with the previous systems, we've been reliant on grad students and postdocs writing code and putting things together. For ZTF, for the Fritz system, with Josh Bloom up at Berkeley, we put together a group of proper software engineers to actually focus it. And so
Mm.
it's a continuous integration approach, and It's done through properly through GitHub and GitHub issues and code review.
So you have proper DevOps, MLOps
Yeah,
pipelines set
yeah,
up for that.
type
Yeah.
stuff like yeah, and that has made so much of a difference.
Mm.
The quality of what we've done has been so much better, and I think um, you know people don't realize how much effort there is behind the scenes to run that, but it really does make so we get lots of unhappy users because they say, oh, this isn't working properly or whatever, but we know what's wrong and they can file something and we can work against it and whatever,
Hmm.
rather than it being some poor grad student who gets the email and then does, so I think, I even for astronomy, I think proper software engineering is so important. And I know, colleagues of mine at Caltech and elsewhere who are looking at big data projects now. They're looking at people, they're hiring software engineers, or they're developing scientific software engineers who understand this. So I think, you can't underestimate the importance of industry practices. And it's called engineering for a reason. It's not just writing a piece of code. There is more to it than that. So I think that's one of the really important lessons that we've learned of seeing the benefit of. Um, I think the other thing is, um, I mean, I say we've actually put out 800 million alerts total to date.
Mm.
Um, Another thing we've seen is, but of those 800 million, actually only 500,000 have been deemed as interesting by someone. So there's a lot of, I don't know what's in the other 795 million or whatever. Um, but
But if
it's
it's a giant black hole, I'm sure you know it.
yeah, it is. But I mean, so there's a lot of so actually the point being though, understanding what makes something interesting is not a
Yeah.
predictable thing. You don't know why something, so you need to have good anomaly detection, but you also need to be able to do good Q&A on why it's an anomaly
Mm.
and understand what's going back to the data, and have easy ways of doing this, and systems which allow you to understand what was going on and why it was detected and things like
Hmm.
that. So I think
That
that's one.
automating what humans find interesting might be a very difficult problem.
Um, yes, I mean you can write down a rule set of what to define something as interesting, but then someone might see something else and go, oh, but that could be as well, and then you go, well, you know,
I'm just
um,
thinking, scrolling Reddit late at night,
yeah,
what people find interesting just varies so much.
yeah, yeah.
Well, let me get to our first question.
Sure.
This individual is curious about much of the tooling and the pipeline that's being developed in-house at Caltech
Yeah.
versus, how much are you buying off the shelf as third party? How much are you building yourself as open source? Or are you hiring out different teams to help you out for specialty areas?
Uh, yes, that's a good question. So the data pipeline is all done in-house at IPAC because they are a NASA data center. They're also part of
Mm.
Caltech, and they're used to doing pipelines for missions and big data archives. So they're the ones who have the on-prem computing to do the data reduction and that sort of stuff. They put the alerts out. Now, the alert management is stuff that we do here in Cahill. I mean, the Fritz system, and uh, we've brought in we've brought in so we've collaborated with a program that Caltech has called the Schmidt Scholar Program, where they train computer scientists, graduating computer scientists, to be scientific software engineers.
Mm.
We've benefited from two or three of those over the years, who've really helped focus and drive particular aspects of the Fritz system. As I said, we're also partnering with Josh Bloom at Berkeley on doing this, and he brought in commercial software engineers as well. So we sort of formed our own little, I don't know what you call it, group. I mean, it's not based at Caltech. It was a little bit bringing people in to do that sort of stuff. But most of it has been, I mean, it's all open source. Um, but we've found that actually, at least for the data infrastructure, most of the off-the-shelf stuff was we could just build it easily ourselves.
Mm,
In terms of machine learning models or AI systems, some of those are a little bit more off the shelf in that, it's someone else's code or they've developed a model and then we just take their code and whatever. I mean, certainly the VGG6 model we didn't come up with, and that was an off-the-shelf
right,
computer
right.
vision model back in the day. And so it's sort of things like that we won't develop the model so much ourselves. We'll just use what's in the literature or, try something that someone else has done, whether it's in astronomy or whether it's in more broad science.
Mm.
I'm always on the lookout for new techniques for whatever. Um, oh, right, they're doing that. Okay.
Now, one technique that we hear a lot about in the ML community is federated learning.
Yes.
Are you able to take any pages from that book?
So, yeah, I mean, we looked at this a few years ago. So, so I've talked about Fritz as our broker system. One thing that we've been very keen on, because we release all these alerts to the astronomical community, they need their own pieces of infrastructure to be able to handle 500,000 alerts a night and find the things they think of as interesting. So there have been a number of brokers, alert brokers, that different bits of the community have developed individually, and they use ZTF as the alert stream. They're all focusing on the 10 million that Ruben will be putting out, but we've been the proving ground, testing ground for that development. Uh, we wanted to do a Ruben broker as well, but we wanted to take a different angle on it. We were looking at edge computing. We
Mm,
believe that with fast enough inferencing, we could very easily handle 10 million alerts a night for a couple of low-level models, which will allow us to filter 10 million down to the 100 that are interesting to whatever. And we believe that we could do that with a Raspberry Pi and an Edge TPU USB plug-in for that sort of thing. And then we were thinking about if we had that and we had a number of other instances like that, we could actually do federated learning. We could say, okay, this has learned this bit and this has learned this bit, and we could send it out. And so we were looking at that as a model. Um, and um, it looked interesting at the time, but it's as you were saying that I gave, I gave a talk in 2008 where I made predictions about what I thought 2020 would look like and
uh-huh.
this sort of stuff. In 2020, 2019, 2020, when we were looking at for it looked the right way. And I
Mm,
thought it would be more of that going on in 2025. And it hasn't panned out that way. Certainly in astronomy, that we haven't seen, lots of little bits of ML or
mhm.
deep learning or whatever running and sort of connecting. So I don't think we're there yet. And I don't know whether it's a problem that we don't have the data flow where we need that yet, or it's just that astronomy is not naturally such a distributed science. I could imagine something like uh, oceanography or a biological science where they've got big sensor networks, where that's a much more so you could have some learning associated with the sensor as well, and then you federate
Mm.
the intelligence that way. Um, and astronomy is just not developed that way. So it's as always with these things, it's a constantly changing environment and a very fast one these days. And so things that looked promising some years ago, it's sort of okay that didn't pan out. And I think the ideas I had for federated learning for the brokering haven't. Now they may still. It may be that once Ruben is up and some market forces or whatever, maybe there are communities, and maybe it's communities in Africa for high school students learning or whatever, where you could imagine they can have a Raspberry Pi that's participating with the alert stream going in and connecting,
Mhm.
and they're doing things in these networks where they're all training and connecting together. It's possible. I don't know.
Well, In closing, if you were to make a prediction where anomaly detection for industry and astronomy, what is the next big discovery or the next big hurdle that is to overcome? We won't hold you to it. This is recorded and it is going out to the world, so just please keep that in mind. But what's your prediction now?
That's really difficult. I mean, we've got so we're at a really interesting point again, right? Because the Webb's James Webb Space Telescope has thrown up all these things which we don't really understand, and you know you see it all the time on. You read your news cycle in the science news saying, "Oh, challenge to the model of this and challenge to the model." We shouldn't see those things there. So there are. I think what's interesting is we are at a point again where there are a lot of interesting questions in science that, or in astronomy where we don't know what the answer is. And you know, the next discovery could be the next discovery could be we finally understand what dark matter is, or we finally understand what dark energy is, or I mean, one of the latest, you know, spectra survey results seems to suggest that, you know, dark energy is maybe not constant, maybe it does change, and we don't know about that result. Or we know that the Hubble constant, which is measuring what the universe expansion is at odds with different ways of doing it, or maybe it isn't, depending who you talk to. So I think there's a lot of, you know, interesting or stuff like that going on. I think in gravitational waves, um, you know, there was a big thing back in August of 2017 when we found the first optical counterpart to a kilonova, two neutron stars merging. And we thought that would be the birth of a new era. And it's actually driven a lot of the science behind ZTF, and the development of called multi-messenger astronomy, where you're trying to combine alert streams from different wavelength telescopes and stuff like that with the gravitational waves. And we haven't seen one since. And the fact that we saw one so early on, we expected to see more. And so I think maybe the next big discovery is actually the next kilonova, because that would be a big thing. We would get a second one then, and we'd know if that was the same as the first one. And Rubin may be a better telescope for doing that. Maybe these things are much fainter than we thought. And so I think that could actually be a really exciting second example of stuff we know is going on, and why haven't we seen them, and what's wrong with what we're doing or our models or our thinking in an important way. Because the belief as well is that these kilonovas are the way that, you know, elements like gold and
Yeah.
mercury and things like that are created and put into the universe. But they're very, very, you know, it's anomaly detection to find them. You're having to hunt through a large amount of data. Now, maybe that they're actually sitting in our data and we've just been looking for the wrong anomaly. And you know, so which would be embarrassing in some ways, I think, but maybe not. So I think if I wanted a safe prediction, I'd say the second kilonova would really be the,
Mm.
you know, the thing that would really help us, and then the third, and then the fourth. But yeah, something like that. But what I think is going to happen is, you know, as Webb has shown us, there's stuff we just don't know that's out there. And I think Rubin, when it starts, and the Roman Space Telescope when it launches next year, hopefully, and it starts doing stuff as well because it has time to make, there's going to be stuff that we didn't know was out
Yeah.
there.
So
And so it's finding the unknown unknowns, which again is anomaly detection.
right, right. Well, I think you just bookended this discussion perfectly with that statement, Dr. Graham. If people want to follow you, if people are interested in your work, how can they do that?
Uh, that's a really good question. Um, well, they can always email me, mjg@caltech.edu. I'm on LinkedIn. I occasionally post. I'm not a great one for social media because it takes time to do it properly.
Right,
And
right.
I'd
No
rather,
scientific discovery while
well,
tweeting.
yeah. I mean, we have so ZTF has a Twitter X stream. We have a newsletter. We put stuff out. Um, I am on some social medias and I do post stuff when we've done it. So that's the way. But I'm always contactable. I'm always happy to for people to contact me and say, "Oh, I'm interested in this. Can you tell me more or point me in?" And
Right.
sort of do it that way.
Great. And for our listeners, if you're interested in some of the courses that Caltech Center for Technology and Management offer, we have a free AI Tools for Everyone. It is going into its sixth iteration where we spend 8 hours, so 2 hours a week, teaching different out of the box AI tools that you can use to become more productive at work and just kind of understand state of the art on what's the market. Dr. Grant, thank you so much for joining us. And
And
for everyone else, we'll see you next month on Making AI Possible. All right. Thanks.